Okay, this represents any square, just this square, not the additional yellow shaded regions, just this square. If I double the edge length of this square, I get another square, and since the edge length is doubled, if I cut that in half, now I've got cut it in half this way and cut it in half this way, I can construct a square the same size as the original, and then I can, of course, construct another one here, another one here, and another one here, which means that I now have 4 squares, each equal in area to the first, so that a square with doubled edges can be covered with 4 copies of the original square. Thus, whatever the area of this original square here, this one here has 4 times its area. So if I plot a graph, okay, I choose any value of x. Let's say I choose this value here, okay, and then I choose any, and I haven't chosen a value of x, I've chosen a point on the x-axis to stand for the side length of this square, whatever that might be. It might be the actual length, which may be 2 inches. It might represent 10 miles by 10 miles on a map. The side of this square could be anything. We haven't labeled any scale here on the x-axis, but I do say that this point corresponds to the length of, let's say, this square. Then this y-coordinate is going to correspond to the area of that square. Okay? And we're going to match up this y-coordinate with this x-coordinate to get a point on the graph of y, which is the area of the square, versus x, which is the side length. Now, if I double x, I come out to here. Okay, now if I've doubled x, then what has to happen to the value of y? We can see from this picture that it's going to have to quadruple. Okay, y is going to have to get 4 times as big. So hopefully this point does a fairly good job of representing that. Then what happens? What if we again double the x, which brings us out to here? And you can ignore this intermediate point here. That's for something else we'll see in a minute. Well, we should get 4 times this area, which would be 1, 2, 3, 4 times as great. Actually, this point is a little high, but I would match up this point here that's 4 times as high as this one with this point here to get another point on the graph. Then I could sketch a curve. And this curve should should represent area of a square versus side length. Okay? Anytime we double the length of the sides, we quadruple the area of the square. So then we ask, okay, what if we increase the side by a length by a factor of 1.5? That means the side of, well, let's take our original square. Okay? If we increase the side by half, that means we have 1.5 times the length. That means the factor between the lengths would be 1.5. So here we have a side length, here we have 1.5 times the side length. Here we have a side length, here we have 1.5 times the side length. And we get a bigger square. Now I want to know what the area of that square is. Well, there's an easy way to do that by subdividing the square, and you can kind of see how I've done it. And that works fine if the factor is 1.5. What if the factor was 1.3? You wouldn't have a really easy way to do this, although you could reason things out. Okay. So I'm going to use the graph to estimate what the area should be if we increase, or what the area factor should be if we increase the side length by factor 1.5. And I just do this by marking the point that's 1.5 times as far from the origin as this one on the x-axis. That would represent a side length that's 1.5 times this one. Now, the area corresponding to this would correspond to this distance on the y-axis, and the area corresponding to the side length, which is 1.5 times this, would correspond to this coordinate on the y-axis. Then the question is, by what factor does the area change? Well, this is about this big. If we do this again, well, we still have about this much left. So what's the factor between this point and this point? It's a little more than 2. Maybe about 2.2. Well, construction here makes it clear that the area of the larger square will be 2 1/4 times the area of the smaller. This rectangle and this rectangle are equal in area, each with half the with a width that's half as great as the length of the original, so we can put these two together to make up the area of the original square. And then this one is half of this, which is 1/4 of this. In other words, we could take 4 of these and put them together and make up this square, and we could construct that. So we know that this bigger square has an area that's 2 1/4 times smaller. So if we had perfectly constructed our graph, our estimate would have, and perfectly estimated, our estimate would have been 2.25 times the area. So what we get here is consistent with what we see here. Now it should be clear that since doubling x increases y by a factor of 4, this is the factor 4 graph. The factor 4 power function graph, as a matter of fact. So this represents the factor 4 power function. And y quadruples when x doubles. Now let's see how we can apply a little bit of algebra to this and get a formula for the area function. Of course, you've already been told what the formula is for the area of a square. You've known that for some time, and hopefully you've been told something about why the formula is what it is. But we're going to do a little algebra and say if y equals c times x squared for some constant number c, then y forples when x doubles. And if we can prove that, then we proved that this graph is represents a y equals c x squared function for some constant number c. What's our proof? Well, we let x1 and x2 be 2 values of x, with x2 equal double x1. And then we let y2 and y1 be what this formula gives us if x equals x1 and x equals x2. So we're going to let y2 equals cx2 squared, y1 equals cx1 squared. Now the factor by which y changes is just y2 divided by y1. And that's going to be cx2 squared divided by cx1 squared. And we divide c by c, we get 1. 1 times x2 squared over x1 squared is x2 squared over x1 squared. And I don't like to cross things out and call it cancellation because people do it wrong all the time. Okay, we get x2 squared over x1 squared, and that's equal to the quantity x2 divided by x1 quantity squared, which is obvious if you understand how to multiply fractions. Now, since x2 equals 2 times x1, then we replace x2 by 2 times x1, leave x1 where it is, so that we have this expression. Squaring everything, we can square the 2, we square the x1, we square this x1, we get 2x1 squared over x1 squared. x1 squared over x1 squared is 1, so our result is 2 squared, which is 4, which means that y has now changed by factor 4, and we've shown that doubling x forples y. So our graph represents y equals cx squared. It has to represent y equals cx squared, and that's before we actually label the scales.